All right, next thing I wanted to do in this video is actually apply this relationship between centripetal force and the universal law of gravitation. So this is a set of practice problems that I'm assigning to you all. I'm going to go through the first question here, and then we'll also go through another example problem. All right, so it says, suppose you are at mission control on the moon in charge of launching a moon orbiting communication satellite. First of all, they're asking us how much would a 1,500 kilogram satellite weigh near the surface of the moon. And remember that weight, so when we talk about weight in physics, weight is a measurement of your gravitational force, or the force due to the interaction of your mass with the Earth. So when you hear the word weight, it's referencing Fg. So this is just F little g or F big G. We could use either equation here. Then sometimes we talk about a feeling of weight. Remember that feeling of weight then comes from the normal force. So hard to keep track of, but a little bit of a difference between what is your actual weight, what's the actual gravitational force on you, versus the weight that you feel. Because, for example, astronauts that are in the International Space Station, they still have weight, there's still a gravitational force on them, but they feel weightless because there's a lack of a normal force as they're in that constant free fall motion around the Earth. Okay, so we want to figure out how much would that 1,500 kilogram satellite weigh near the surface of the moon. So in that case, we're just on the moon and you have your little satellite thing. And so if it's near the surface of the moon and we want to calculate its weight, we're just quantifying what's the gravitational force acting on that satellite when it's on the surface of the moon. So that would be gravitational constant times the mass of the satellite times the mass of the moon, and then divided by their separation distance, which in this case is going to be the radius of the moon. So radius of the moon, and then remember that in this equation, the radius is squared. And then it's just a matter of plugging in values. So I'll just cruise through that here. All right, so 2,428.9 newtons of weight that the satellite would feel on the moon. For a comparison, just real quick, remember that if you wanted to get the gravitational force or the weight on Earth, you'd be taking that 1,500 and then multiplying by 9.8. So on the Earth, this would have a weight of 14,700 newtons, which is obviously much larger than on the moon. All right, so the satellite is supposed to have an altitude 100 kilometers above the moon's surface. What is the distance between the satellite and the moon's center of mass when the satellite's in orbit? So now we have our moon, and we're going to put the satellite in orbit around the moon. And so the distance here is going to be 100 kilometers. Basically this question is asking for what's our new r here. R then is going to still be the distance between the two center of masses. So we have to incorporate the radius of the moon into that separation distance. So it would be the radius of the moon, moon, plus the 100 kilometers, but note that this is in kilometers and the radius of the moon here is in meters. So let's just make sure we convert the kilometers into meters. So radius of the moon, and then 100 kilometers in meters is 100 times 10 to the 3. Remember, you just can add that factor of 10 to the third to do a quick conversion there. So 1.84 times 10 to the 6 meters. So now we want to quantify the centripetal force when it's in its orbit. Centripetal force when it's in its orbit is, so satellite, moon. Right, remember the centripetal force is that combination of radial forces, and in this case there's just a inward gravitational force that allows the satellite to continue orbiting around the moon. So that is its centripetal force is just Fg at this new radius. So Fg still is g, the mass of the satellite, times the mass of the moon divided by this radius, new radius here, squared. All right, so I got 2,172 newtons. A little quick check, maybe think to yourself, should this force be greater than or less than the force, the gravitational force on the satellite when it's on the surface of the moon? Since it's further away, it has a longer separation distance, we would expect that this force would be weaker further away because there's our radius in the denominator. All right, part D, find the required orbital velocity for a satellite to maintain the orbit at a distance 100 kilometers above the surface of the moon. So same distance here, so same gravitational force. But now we're asked to find the velocity. So this is where we're going to use kind of this side of the equation, that the velocity is really part of the acceleration that it experiences with this much force. So this is going to be equal to the mass of the satellite times the velocity squared divided by that radius. Again, just plugging in numbers here and calculating. All right, so we do need to do a little bit of algebra arrangement here. First thing I usually do is get anything out of the denominator. So I would multiply both sides by this 1.84 times 10 to the 6th factor. So that'll eliminate it on this side. And then in order to get velocity by itself, I have to divide both sides by 1,500 kilograms. So that means on this side, I'm dividing by 1,500. So that means that's going to be away there. And then the last step is going to be to take the square root to just find the velocity. All right, so I took the square root. I got a velocity of 1,632.3 meters per second that this satellite would be moving around the moon. Okay, new vocab word here about orbital period. Orbital period always just refers to the amount of time for one complete orbit. For example, the Earth's orbital period around the sun is 365.25 days. So now we're going to find out how long does it take for this satellite to make one complete orbit of the moon. This is just going back to an equation that we used actually right at the very beginning of this unit. Remember that this velocity here is really just the average speed along that along the object's orbit. So this is really the average speed. The velocity is changing because we're changing direction here, but the speed doesn't change. So in this equation, it's really, I was talking just about the average speed. So the average speed would just be the distance that it's traveled over the amount of time that it takes. And I'm going to use a big T here because you often see a large T to represent the orbital period. So the distance that the satellite makes during that rotation here is really that it's just covered that full circumference of the circle. So the circumference is going to be given by 2 times pi times its radius, the distance between where it's rotating and the center of the moon, and then divided by that orbital period. So since we know the radius, we know the distance, and we know the velocity, we'll just have to solve for orbital period here. Okay, so t is in the denominator here, so I'm going to move it into the numerator by multiplying both sides by t. I just had the thought that maybe you couldn't see that in my screen. So I'm shifting this up, and hopefully you can see everything now. If you missed that before, here's our average speed, and then it's given by circumference divided by that orbital period. And then I've just plugged in numbers, and I've multiplied by t on both sides so that my orbital period ends up out of the denominator and easier to solve for. All right, so we get an orbital period of 7,082.7 seconds. Remember that this is going to be in seconds because our velocity was in seconds. Hard to make sense of that number for my small human brain, so I would probably convert that into maybe hours. Let's do that real quick. So it takes 1.97 hours, or about 2 hours, for this satellite to make one orbit of the moon there. I am going to do one more practice problem for you here, because it's just a slightly different problem from that first example, and more similar to maybe what you'll see moving forward or in the rest of the worksheet there. So this is actually also really interesting because this is how we know what the mass of the sun is, using kind of these theoretical equations, but these equations that we've seen to hold true, just like the data that they collected on how fast each of the planets is moving relative to its distance from the sun. So, maybe we want to know what is the mass of the sun. Why might we want to know that? Well, if we know the mass of the sun, we can calculate about how much hydrogen and helium might be in there and have a sense for maybe its lifetime or how long it will take before the sun is out of hydrogen to continue fusing. All right, so we're going to determine the mass of the sun given the following information. So we know that the Earth orbits the sun once every 365.25 days. And we know that the distance from the Earth to the sun is 1.507 times 10 to the 11th meters. On average here, everything is kind of using the average distance. The Earth's orbit is slightly elliptical, and so you could do a more accurate calculation here using the equation for an ellipse instead of just the equation for the circle. But for our purposes, we'll use the equation for the circle. All right, well, we want to know the mass here of the sun. First thing is that most of these questions are going to be using the universal gravitational law and also this centripetal acceleration. So if we think about the forces that are acting on the Earth in its rotation here on the sun, we just have the gravitational force. So the net force and the centripetal force that's acting on the on the Earth is just the gravitational force on Earth by the sun. So that'll be equal to gravitational constant times mass of the sun times mass of the Earth divided by their separation distance squared. Then we know that net force causes the acceleration, so the Earth to accelerate, have this change in its velocity, and that acceleration is also given as its speed squared divided by the radius at which it's rotating. So here's our centripetal force, and here is kind of the result that it causes the acceleration. So these can be set equal to each other because they both represent the net force. So yeah. All right. First thing to notice is that mass of the Earth appears on both sides in the numerator. So that means this mass of the Earth is independent. So we could use Mercury for this or a different planet, but we're just choosing to use the Earth. Other thing that we've seen before is that since there's a factor of r in the denominator on both sides, that when I multiply both sides by r, it means that this r just becomes 1, and here the r squared becomes just r. So now at this point, we have that g times mass of the sun divided by r is going to be equal to the velocity of the Earth squared. Now, the variable that we're looking for is mass of the sun. So let's rearrange the equation so that mass of the sun is by itself. So we'd have mass of the sun is equal to, let's see, I'm going to multiply by r on both sides and then divide by g. So I get v squared times r divided by g. So g is just a constant, that one we know. The separation distance was given, so we have that here. Velocity wasn't explicitly given, but we do know how long it takes, this orbital period, for one rotation here. So let's do a little side note to calculate the velocity, because we know that velocity is going to be that distance over the time. So we have the circumference, 2 pi r, over the orbital period here, which was given. So let's start by maybe just plugging in. But for the orbital period, remember that any time should be in seconds unless we're reporting it as our final answer. So let's do a little side note, and we're going to convert 365.25 days into seconds with a little dimensional analysis. One thing I'll note on this calculation, since you're dividing by something that has a factor of 10, remember you should always use the parentheses in the calculator for that, even if it's not being squared. So I've added, I had my answer for the numerator, and then I did divided and then added the parentheses. Or you can use Desmos and make sure it calculates for you. So the speed of the Earth, on average here, what I have at least is 30,002.4 meters per second. What would have been better if I'd carried more significant figures here in the seconds, because I ended up rounding quite a bit just to speed up the calculation. Note that we'll have some differences in how we calculate these values because of just rounding differences. The more sig figs you can carry, the better, but obviously sometimes we all get lazy depending on how important it is that our answer is accurate. Okay, but regardless, now I have the velocity, so now I can calculate the mass of the sun here. So mass of the sun is that velocity squared times the radius again, divided by the gravitational constant. And we end up with a mass for the sun of over 2 times 10 to the 30th kilograms.
So there's one other thing I wanted to point out with this practice problem, the first one that we did. In it, on part D, we actually calculated exactly how fast the satellite needs to be moving in order for it to maintain that circular orbit around the moon. That is the only velocity that it could be holding at that orbit. If it's going any faster, that means that it's no longer going to be a circular orbit and that it would become more elliptical. And maybe if it was going even faster at a certain speed, it would escape the gravitational force of the moon and actually just keep moving in a circle, keep moving in a straight line until it's affected by some other object in its gravitational pull. Or if it was moving any slower, it would end up kind of spiraling and actually going into the moon and landing on the moon. So this is the same for the satellites that are circling Earth. There are so many satellites going around Earth. I know that for just the GPS system that we use in the US, there's 60, and there's at least 3 other major GPS systems. I think the one that's based out of Russia uses 120 satellites instead of just 60. So there's many, many satellites going around Earth, and the speed at which they're orbiting Earth has to be really specific, depending on exactly how far away those satellites are from Earth's surface. So I want to show you that demonstration back to using our rubber stopper that we used for the lab earlier this week. Because this model actually does work for anything in circular motion, and one of the nice things about this demonstration is that it's still using gravitational force as the main force that's affecting the spinning object or the rotating object here, so the rubber stopper. So at a particular radius, so this is like the satellite orbiting around the Earth right here, and the Earth exerts a gravitational force on that satellite. So that's like the mass hanging down that's still exerting a gravitational force. So I can get it moving, and it can maintain a certain speed at that radius, and there's really only one speed that can be. But if it's rotating any slower, so if we slow down that rotation, we'll notice that over time, it's getting closer and closer until it actually collides with the Earth. So this demonstration works exactly as a satellite does, orbiting the Earth. It would collide with the Earth if it was moving any slower.